Okay, so we're going to try and find a Taylor series for ln of x. We'll let that series centered at a equals 2. So we'll start out with our usual list, n, the nth derivative of x, and the nth derivative at our point, at our center, which in this case is 2. All right, so let's get busy with that. 0, 1, 2, 3, 4, 5. I think that should probably do it. So our function is just ln of x. And then this is going to be an ln of 2. Nothing special there. The first derivative, I'm hoping that you're familiar with that. That's just 1 over x. And that would be 1 over 2 here. But for the rest of these derivatives, you might regard it as being helpful to think of this as being x to the negative first. That way you can just use your power rules to differentiate this. So the next derivative is going to be negative 1 x to the negative second. And how about the derivative after that? Well, actually, you know what? We should probably evaluate the function. That's going to be negative 1 over 2 squared. Negative 2 times negative 1 is going to be 2 x to the negative third, or 2 over x to the third, or it's going to be 2 over 2 to the third. And I know that these will simplify, but I don't want to do that just yet. How about the fourth derivative? Negative 3 times 2 times 1, x to the negative fourth. So negative 6 over 2 to the fourth. And finally, the fifth derivative, negative times negative is positive, so 4 times 3 times 2 times 1, x to the negative fifth. It's going to be 24 over 2 to the fifth. All right, so we're going to have our work cut out a little bit in terms of finding a series, a pattern for this series, so you can write it with a nice summation. I'll call it T of x. T of x is going to be ln of 2 divided by 0 factorial, which you don't have to write that if you want, times x to the 0. I'm not writing that. Then the second one is going to be 1/2 over 1 factorial times x minus 2 to the first power. So it's your function divided by 1 factorial, and then the function at 2 divided by 2 factorial, and so on. These are the numbers that we need. So I'm going to kind of pause here for a second and let you try and race ahead of me. Try and write down a few of these next terms. If you want, pause the video if you're watching this later. For those of you in class right now, try and get ahead of me with these next few terms. Okay. How are we doing? Is yours matching mine? Let's take a look here. So it should be something like this. You should be taking the value of the function, dividing by the corresponding factorial, times x minus 2 to the corresponding power. These numbers should match. 0 factorial is just 1. Now the 2's in these denominators I'm going to bring down. Notice that our series is going to be alternating. So we've got a negative here, negative here, negative, positive, negative, positive. Okay, looking good. So the next one would be negative, etc. The 2 to the power I'm going to bring down to the denominator. So it's going to look like this. ln of 2 plus 1 over 2 to the first times 1 factorial times x minus 2 to the first minus 1 over 2 squared times 2 factorial times x minus 2 squared plus that 2 in the numerator I'm going to let stay. So it's going to be 2 over 2 cubed 3 factorial x minus 2 cubed. And I'll let some of these hang around because they're going to give me some cancellation that I'm going to want to see. 2 more terms. The 6 I'll leave up in the numerator. 2 to the 4th comes down to the denominator. So minus 6 over 2 to the 4th, 4 factorial, x minus 2 to the 4th, plus 24 over 2 to the 5th, 5 factorial, x minus 2 to the 5th. Now, what you can see in writing it like this is that we're going to get some cancellation. This is really 2 factorial. It's going to cancel with most of the stuff in 3 factorial. This is our 3 factorial. Is going to cancel a lot with 4 factorial. And finally, 4 factorial will cancel mostly with 5 factorial. In fact, the only thing we're going to be left with is a 3, a 4, and a 5 when we do that cancellation here. Obviously, there's nothing much there because 1 factorial is just 1. Before I move on, are we okay with where we're at?
Yeah.
Thank you. Thank you. All right, so this is going to be ln of 2 plus 1 over 2 times 1 factorial, x minus 2, minus 1 over 2 squared, 2 factorial, x minus 2 squared. That and that will cancel, leaves me with plus 1 over 2 cubed times 3 times x minus 2 cubed. And I think I'm starting to see the pattern here. So the pattern is that this power of 2 and this exponent here are going to match. So the next term is going to be, let's see, plus, minus, plus, minus. So it's going to be minus 1 over 2 to the 4th times 4, x minus 2 to the 4th power. And then finally, plus 1 over 2 to the 5th times 5, x minus 2 to the 5th, and so on. But that's enough for me to decide the general pattern. Now, what's a little bit different about this one is that first term. That first term of ln of 2 does not fit into our pattern at all. It's just this red-headed stepchild that just doesn't fit anywhere. So sorry, ln of 2, you're out of luck. So it's going to be ln of 2 plus the sum from n equals, well, let's start our series at 1 since I got a 1 here and a 1 here. 1 to infinity, -1 to the n plus 1. If I put an n plus 1 here, is my first term going to be positive or negative? Does it match? Sign. 1 plus 1 is 2, -1 squared is going to be positive. So those two match. So we're good there. We're going to have a 1 over 2 to this power. So 1 over 2 to the n. And I shouldn't be writing these as factorials anymore. So it'll just be times n, x minus 2 to the n. And that's your series. You just kind of stuck with this term out in front. That's okay. So that's your Taylor series polynomial. How are we looking on that one? Hey, there's good news. We're almost halfway done. Don't forget, we got to figure out the radius of convergence, and that'll lead us to the interval of convergence. So still got a little bit of work left to do. Now, as far as the convergence is concerned, we're concerned with the convergence of the series. I don't have to worry about ln of 2. That's just a constant out in front. That's fine. So find the interval of convergence. All right, so a little bit of work to do here. For that, we generally go to the ratio test. So I want to calculate the absolute value of a sub n plus 1 divided by the absolute value of a sub n. And just an n there, would please. Okay, sub n. A sub n plus 1. Now we're working with the absolute values. I'm not going to worry about the -1 to the n term because the absolute values will take care of that. So that's going to be 1 over 2 to the n plus 1 times n plus 1. And this x minus 2 to the n, let's put that up in the numerator. So it's going to be x minus 2 to the n plus 1 times the reciprocal of this, which is our a sub n. So let's just make clear that that's your a sub n. This is your a sub 1. So the reciprocal is going to put a 2 to the n here times an n, x minus 2 to the n here. And all this is still in absolute values. Most of this is going to cancel. I've got n of them here and n plus 1 of them here. So all but one of them is going to cancel. Likewise, all but one of these is going to cancel. So that's going to leave you with x minus 2 times n over n plus 1, 2 times n plus 1. Okay. Now the x minus 2 and the 2 here, I can factor those out. absolute value of x minus 2 over 2 times absolute value of n over n plus 1. All I did was I calculated this and I simplified it. Now I want to take a look at its limit as part of my ratio test. The limit as n approaches infinity of a sub n plus 1 over a sub n. So this part is good review because the ratio test was part of section 10.9, or excuse me, 11.9. We went over that there. Since we're taking a look at the limit as n approaches infinity, and none of this has anything to do with n, I'm going to factor it out. It's going to be the absolute value of x minus 2 over 2 times the limit as n approaches infinity of n over n plus 1, like that. Ooh, wow. What's this limit?
1. Infinity over infinity.
Yes, so it's going to be the absolute value of x minus 2 over 2 times 1, or just absolute value of x minus 2 over 2. And I want this to be less than or equal to 1. Well, I can take the absolute value of 2, and the absolute value of 2 is 2. If I multiply both sides of this inequality by 2, the 2 on the left is going to cancel out. I'll be left with absolute value of x minus 2 is less than 2. In particular, if they just ask you for the radius of convergence, that's it. Radius of convergence. If all they're asking you for is the radius of convergence, you're done. If they ask you for the interval of convergence, then you're not done. To get the interval of convergence, let's solve this inequality by repeating it. So it's going to be negative 2 is less than x minus 2 is less than 2. And if I add 2 to all three parts of this inequality, 2, 2, and 2, I end up with 0 is less than x less than 4. So that's my interval of convergence. Am I done?
No.
Not if you want to try and get all the points possible. No. What else do I have to check, gentlemen?
Convergence, if
The
it
endpoints.
converges or diverges at those x points.
At these endpoints, we've got to check it. So let's do that. So make sure we get all the points. Before I go ahead and check those, are we okay with where we're at on this problem so far? So to kind of recap, we found our series, we found the general term, it looks like this. And then we're finding the interval of convergence using the ratio test. So for the ratio test, we found a sub n plus 1, which is this term. Dividing by this is like multiplying by the reciprocal. We got some simplification. So I simplify this out. I split this up here and here because this depends on n and this doesn't. So when I take a look at the limit here, limit of this term, a sub n plus 1 over a sub n, all of that factors out in front. I just have a simple limit to deal with. Could I use L'Hopital's rule here if I really wanted to?
Yes.
Sure. It's like swatting a fly with a sledgehammer, but it would work. In any case, you get a limit of 1 times this. We solved our inequality. We got our interval of convergence. From now, we just got to check the endpoints. All right, so let's check our endpoints. The series that we want to look at is this one. Sum from n equals 1 to infinity of -1 to the n plus 1 times 1 over 2 to the n to the first power, really, x minus 2 to the nth power. Let's check at x equals 0. So 0 less than x less than 4. At x equals 0. At x equals 0, I get the sum from n equals 1 to infinity of -1 to the n plus 1, 1 over 2n times n and then at 0, this simplifies to the sum from n equals 1 to infinity, -1 to the n plus 1 divided by 2n times 2 to the n times n. And this much is -2 to the nth power. -2 to the nth power. And I can rewrite -2 to the nth power as -1 times 2 to the nth power, or basically -1 to the nth times 2 to the nth. So it's going to be -1 to the nth times 2 to the nth, like that. Does that help me at all? Can I simplify this in any way?
You could cancel out the 2 to the n's.
And the
Perfect.
-1 and
Let's be careful about the -1 to the n.
because it's in the numerator.
It's in the numerator, yeah. So what's going to happen with that term in the numerator is this. This and this have the same base, right? So you add their exponents. N equals 1 to infinity, -1. What happens when I combine these? What do I get when I add these together?
This is a 2n plus 1.
Thank you. 2n plus 1. Nice. 2n plus 1. Now, we've run into 2n plus 1 before. What did I tell you about a term like 2n plus 1?
It's an odd number.
It's always an odd number. Perfect. That's exactly what I wanted. And this is always an odd number. Then you know what? These signs aren't going to alternate. This is just going to be sum from n equals 1 to infinity of -1. I mean, you can test it for yourself. If you write out a few terms at n equal 1, oh, that's the third power. All right, so that'd be negative. N equal 2, oh, that's the fifth power. It'd again be negative. 3, 7, etc. It's always going to be an odd power here, so it's always going to be negative. What do I know about the convergence of that series?
It's a P series.
Yeah, it's a P series. So this is why I keep on pushing that 2-minute drill, is because when you get to this point, you just got to decide, all right, is that converging or diverging? This diverges. It's the negative of the harmonic series, or better yet, diverges, P equals 1, done. So we're not going to get convergence here, all right? let's test at the other endpoint. So at x equals 4, let's see what happens there. So I'm going to plug 4 in for x. I'll get 4 minus 2, which is 2 to the n. And let's just see what happens. Negative 1 to the n plus 1. 2 to the n times n. So if I put in a 4 here, I end up with the sum from n equals 1 to infinity of negative 1 to the n plus 1 times 2 to the n over 2 to the n times n. Kind of like the last one, you have a 2 to the n term that cancels out. So it can leave me with the sum from n equals 1 to infinity of negative 1 to the n plus 1 over n. Does that one converge or diverge?
Converge.
Does that converge?
Converges. Can you tell me why?
Because the alternating series test?
Yep. Converges by the AST. Alternating series test. Done. But you know, now you can see the benefit of getting better at looking at these series and just knowing. It's because part of these problems is to come up with the interval of convergence. 0 is less than x, less than or equal to 4. So the series should converge, you know, near 0, but not to 0, and it should converge actually at 4. Wow. All right, we did a lot here. If there's something you want to look back at, something that maybe I went over a little too fast, now's a good time for some help. All right, I'll give you another chance in a minute. Let's just actually take a look and see what it means that it converges in this interval. So here's your function, ln of x, and we expect convergence, you know, pretty good convergence near 2. So let me zoom in on this a little bit. There we go. So there's the center of our interval of convergence. Here's one of the endpoints. The other one is down at negative infinity, so we won't be able to see what's going on there. But let's take a look at our Taylor series polynomial. That's up here at k of x. And let's increase the degree. And increase it, increase it. And you see right away, I mean, just after a couple terms, your convergence is looking pretty good. I mean, after 6, 7 terms, look, we've got convergence. It looks like it's almost converged right here, meaning the value of our polynomial and the value of the function at x equal 4 are almost identical. So you are getting convergence at 4, but not beyond that. No, nothing beyond that. And of course, the function itself is undefined at 0, so it makes sense that our Taylor series doesn't converge near 0. All right. One more try here. This is a long problem. We went through a lot. So if there's something on this that you're like, all right, way back here, can we look at this? I'm fine with that. Give me a shot.
On WebAssign, this would be
Yes.
like parentheses 0 and then 4 and then like a bracket, right?
Yes, 0,
Okay.
4. If they ask for it in interval notation, then they generally do. It look like that, yes. Thank you for the question. Okay, don't worry. I usually only put like 6 or 8 of these on a final exam, so should be a breeze. All right. Oh, yeah, that was a long one. That was the only problem we've done so far in the second part of class. It's 3 pages, at least for me. Now, you don't always have to build up series from scratch. Now, there's a lot of known series, and these are your known series. We've developed some of these things. Here's e to the x, here's sine of x, cosine of x, arctan, natural log. We developed that one. The binomial series, this one was discovered by Newton during the plague years when he's home alone. So you can identify with Newton. Newton went through a plague in 1664 and 1665 that closed down his college completely. I don't know why they didn't go remote, but they didn't. So bad on them. But in any case, it's when Newton discovered the binomial theorem for non-integer values of k. But let's take a look at something that we know and make these problems a little bit easier. So take note of that series for cosine of x. I'll write it down in just a second here. But example F. You guys ready for an easier problem?
Yeah.
No? Yes? Oh, okay. All right. I wasn't sure. I was like, oh, all right, I can take out a harder one. So we're going to look at the series by substitution. Do a couple problems like this, series by substitution. And our first problem is to find a series for f of x equals x squared times cosine of 4x. Okay, so let's start by this. NB stands for nota bene, or pay attention, note well. We'll start out with the series for the cosine of x, sum from n equals 0 to infinity. Now, cosine is an even function, so -1 to the n, x to the 2n over 2n factorial. So, in fact, if you integrated this, you would exactly get the sine function, the series for the sine function. Okay, but we don't want cosine of x, we want cosine of 4x. So cosine of 4x, sum from n equals 0 to infinity. And so what we'll do is I'll substitute in that 4x. So here we go, 4x. And that should be to the nth power for that 1 here. Let's clean this up. That's going to be 4 to the 2n and x to the 2n there. So the sum from n equals 0 to infinity, -1 to the n, 4 to the 2n, x to the 2n, over 2n factorial. Okay, well, we're pretty close. The only thing left that I needed, I still don't have, is that x squared term. So I want to find something for that. So I got cosine of 4x. And then I want to write this x squared here. And I can take this series, sum from n equals 0 to infinity, -1 to the n, 4 to the 2n, x to the 2n, over 2n factorial. I'm just going to write the x squared out in front here. But then I'm going to distribute that in. This is going to multiply each of the terms in my series. And in particular, when I multiply x squared times x to the 2n, the exponents are going to add. And so my final answer should be this: the sum from n equals 0 to infinity of -1 to the n, 4 to the 2n, x to the 2n plus 2 over 2n factorial. And that's it.
That was easy.
All right, maybe it wasn't terribly easy, but compared to the previous one that we spent 30 minutes on, it was pretty easy. But that's it. And that's kind of nice that you can take these known series and help develop other terms. So how are we doing on that one?
Definitely better than the last one.
Yeah, definitely better than the last one. Well, speaking of the last one, something we did in the last one was we found the radius of convergence. Actually, we found the interval of convergence, but let's find the radius of convergence for this one. So let's find the radius of convergence. So what interval is that good for? Before I work on that, are we okay with what we have so far in example F? So that's my term a sub n. I want to find and simplify the absolute value of a sub n plus 1 divided by a sub n. Now, because I'm dealing with the absolute value, I'm going to openly ignore the -1 terms. And let's start by writing a sub n plus 1. Now, when you put in n plus 1, if I put in n plus 1 as opposed to an n, that'll be 2 times n plus 1, or it'll give me 4 to the n plus, or 2n plus 2. Do I have any room for that someplace? Yeah, 2 times n plus 1 equals 2n plus 2. Note. So as I do the first term, a sub n plus 1, I'll have 4 to the 2n plus 2. If I put in an n plus 1 there, I'll have 2n plus 4. Over 2n plus 2 factorial. Times the reciprocal of this term, which is going to be 2n factorial, 4 to the 2n, x to the 2n, like that, in absolute value. So I'm going to rearrange these terms to make our simplification a little bit easier to follow. Are we okay with this? I didn't show too much detail in finding these. If you need me to go back and show some detail, I'll be happy to. Were you able to keep up with me as I did that? You put in an n plus 1, and that 2 has to multiply the n plus 1. So I get 2n plus 2, just like right here. Putting in the n plus 1 there, I get 2n plus 2, plus the 2 I had already gave me 2n plus 4. All right, so let's rewrite this. I'll write that as 4 to the 2n times 4 squared, x to the 2n times x to the 4th, (2n factorial). And I want to be really careful and clever with this 2n plus 2 factorial. It's going to be 2n plus 2. And then as I realize that this is a factorial, what's the next one below that?
2n plus 1.
2n plus 1. And then 2n, and then 2n minus 1. But you know what? Let's stop there. Why am I stopping here? Because these two, yeah, those two cancel. At that point, I'm like, hey, I can get rid of those. In fact, I can get rid of a lot of stuff at this point. I can get rid of this, and I can get rid of this.
So, Professor?
Yes.
Aren't you supposed to have, for the second quotient, 4 to the 2n times x to the 2n plus 2?
Yes, 2. X to the 2n. So that's going to leave x squared there. Thank you. Yeah, I lost track of it too. All right, I think we're good here. That's going to leave me with absolute value of x squared over 2n plus 1 and 2n plus 2, or 2n plus 2 and 2n plus 1. And there's also a 16 up here in the numerator. Now the good news is that this part doesn't depend on x, or doesn't depend on n. And if we look at the limit as n approaches infinity of a sub n over a sub n plus 1 over a sub n, n approaches infinity, that's going to be 16x squared over 2n plus 2 times 2n plus 1. I don't need the absolute values because 16x squared is positive, and as n approaches infinity, that's going to be positive. This, if you want to, can come out in front. 16x squared, limit as n approaches infinity. 2n plus 1. Sorry, I ran out of room here. What's this limit going to be?
0.
0.
Yep, it's 0. So if this limit is 0 regardless of x, what's that saying for the radius of convergence? Does anyone remember we did a example or two like this in section 11.9? Radius of convergence is everything. Doesn't matter what x is, these terms are eventually going to go to 0. So the radius of convergence is everything. And your interval of convergence will be negative infinity to infinity. Ooh. How's that one look? Any wrap up on problem number F here? Okay, maybe I should take a quick look at it. I think the first part went okay. We just substitute in for our series, substitute into the series for cosine, substitute in 4x, and then multiplied by x squared. I took that x squared in here by multiplying these by adding their exponents. So I added 2n plus 2 term. And then the second part was just to find the radius of convergence. When you get a radius of convergence, or when you do this ratio test and get 0, so it's independent of x, that means your radius of convergence is infinity. It converges for everything. It doesn't matter what x is, this is going to 0. Your series is going to converge. So that's kind of cool. All right, let me finish up before our next break with this one. And I'm going to do something unusual here. I'm going to ask you to put down your pencils for a second. Just sit back and relax. I'm not really going to hold you responsible for this one. You remember what I is? Remember what I, in terms of complex numbers, represents?
Real number or something?
Imaginary.
Square root of -1.
Yeah, square root of -1. All right, so let me see if I can't find something here. Yeah, this is cool. We'll look back at this in a minute. Let me go back to here. So I is the square root of -1. And the cool thing about that is if you square I, you get -1. I cubed is -1, I to the 4th is 1, so cool. Let's take a look at what happens when we plug in to the series for e to the x. When the series for e to the x, we know it's this one here. It's the first one we derived as example A. So if I put in I times x, and let's see here, right here. If I put in I times x, I get this. Now let me expand that a little bit. I've thrown out the first 9 terms here, but you can kind of see that you're going to get some simplification, like I squared, that's going to be -1. I to the 4th, that's going to be +1. I to the 6th, -1. I to the 8th, +1. And these other ones are going to be either I or -I. So we get something like this. And I've split it up in a couple ways. Stuff that doesn't have I, I've underlined in orange. Stuff that does have an I, I've underlined in green. So let's pull those two together. And you get something that looks like this. And something like this. And I factored out the I from all of these terms. Do either of these series look familiar? They both could, one should. No, maybe not terribly familiar yet. This is still kind of new for you, I guess.
Sine and cosine, maybe?
Yeah, sine and cosine, exactly. This is a sine, this is the cosine. So if you rewrite those series, this is I times this, that's your sine. This is your cosine. So, wow, what's that saying? What that says is e to the ix is cosine of x plus I times the sine of x. Wow, that's brilliant. It breaks this up into a real part and an imaginary part. But wait, it gets even better. Now, let's take and plug in a value for x. How about an important one, like pi? What if we plug in a pi here? We get e to the I pi is cosine of pi plus I times the sine of pi. Now what's the sine of pi? Make me look good here.
0.
Sine of pi is 0. Cosine of pi is -1. So I get e to the I pi is -1. Or if you move that to the other side of this equation, you get this beauty. Wow, that's a sexy looking equation. That's cool. The 5 most important constants in math all in one simple equation, e, I, pi, 1, and 0. Absolutely the Fab Five there in terms of mathematical constants, all in one equation. So cool. In fact, so cool, the writers of The Simpsons included that in an episode called Money Bart or Moneyball. And if you look very carefully, right here, e to the I pi equals 0. One of the books she's studying, along with, I think one of the other ones was Schrodinger's bat. If you've taken any physics, you might get a laugh out of that. So anyways, pretty cool. Thank you, thank you, thank you. All right, that's good enough. I think you're ready for a break. Any questions or comments on that one? Anyone else think that's kind of cool or amazing?
That's cool. Yeah.
All right, cool. Thank you. Let's take a break here. I'll see you in about 6 or 7 minutes.